Good morning. My name is Jim Osterloh. I'm working at M7 Technologies in Youngstown, Ohio, and I'm their Director of Technology and Integration. We've got a project that's funded federally by the Army Research Lab and at the state level by the Ohio Third Frontier Foundation. Go ahead and play that and just let it play. The target of our project is to do in-situ verification, do in-situ setup of part coordinate systems, et cetera, and do it in a model-based fashion. State-of-the-art right now is actually a Renishaw strain gauge touch probe. It's running on the left. And what we're demonstrating right now is a video showing establishing the Cartesian coordinate systems for the part, hitting all the datum planes. On the left side, we're doing with a touch probe. On the right side, we did it with the laser. And you can see the timer. We're cutting apart for about a minute before the touch probe has even established the coordinates. What I want to do in the presentation, I know this has been an objective for a while, and there'll be a lot of skepticism about just how well it works, how did you synchronize it, what's your accuracies, et cetera. And so there's a team of us inside here that have watched it evolve, and they understand that. But I need to take you through those first steps to show you some synchronization detail and what we're doing, and then go into the larger aspect of how do we do it in a model-based enterprise, what's the value edges, where do we create value.
Pardon the interruption. Your conference contains less than 3 participants at this time.
So turn it off. Right? Where do we create value, et cetera. So next slide, please. The only way to really capture this presentation is with a whole lot of video. So after our Christmas party on Friday, Jason and I drank a bottle of rum till 5 in the morning and got up and worked on this thing all weekend. The motivators, you saw it on the left. Touch probing is incredibly slow. Machine owners, asset owners, don't want their chip makers touching parts to capture a handful of digits, statistically insignificant number of points used to set up a datum is one thing. That's common practice. The scene is common practice to find the datums. The real censure is how do you measure the part in the machining center after you've cut on it? Maybe it's not final pass, but how do you measure the part in the machining center so you can maybe get closer to nominal, or you can check your tolerances before you break setup, take it to a QC lab, decide, oh shit, we're a little bit out of square, but I got enough material here I can fix it. Now I've got to go back to the machining center, reset up my datums, but now they're even more critical because I've only got 3 thousandths of material to take off, right? So it gets terribly expensive, and we have national assets, machining centers, that really need to be optimized. We can't afford to do this the old way. We have to find a new, faster means to do it. So overall goal, increase asset effectiveness, do in-situ measurement, and facilitate closed-loop control. Machine kinetics are relatively easy to predict and monitor, but your tool is imparting a pressure. That pressure's got a reaction both ways. The part moves, the tool moves. What's the net result? The part's out of shape. It's out of shape, and it's probably out of form. So what if you could put a closed-loop detection system in there and measure what your deviation from nominal cut path is, and then have an automatic tool path come back and give you your nominal? That's a big stretch, but unless you have a tool that measures really high fidelity data, easy here, we got chords. You're not going to get there. Enablers, we have to have a digital model. I can't run these complex tool paths and compare them with nominals with point clouds without a model. I have to have really high-speed metrology instruments. I have to be able to communicate data back and forth between the machine and the sensors at a really high rate. And to break the ice, I need a machine tool manufacturer that's capable, that sees the vision, that's cooperative, and is motivated to work with us. And that company is Metrology. We happen to have a couple of their machines on our floor at M7. And when we called Paul Wichert and said, hey, we'd like to work with you guys, he took our call because of some other things going on. But you know what? He jumped right on the wagon. He saw the value in it. That was in July. And everything I'm going to show you has been developed essentially since July. So with that, I'd like to introduce Paul Wichert. And I don't want to change the mic, so I'll just be quiet.
Thank you. My name is Paul Wichert. I'm the Vice President for the Machine Tool Group of Liberty Diversified International. A couple of things. I think it's important what Jim mentioned. Had it not been for Vice President Biden walking into M7 for some campaigning, standing in front of a Metrology machine, CNN capturing that video, me in the gym at 5 o'clock in the morning watching CNN, I might not have taken the call by Mike Garvey that incepted this project. Born in the USA, that was an interesting tagline we developed. It took 6 months of arguing between legal and marketing within our company, but finally Bruce said, it's okay, you can use Born in the USA. Go ahead. We're a privately held U.S. company. We've been in business since 1973. We're going to celebrate our 40th anniversary next June. We have manufacturing facilities in Waconia, Minnesota, that's a suburb of Minneapolis, Taichung, Taiwan, and Jinan, China. We're an operating unit of Liberty Diversified International. It's a privately held Minneapolis-based company that's well diversified into different manufacturing disciplines. We were acquired by LDI in 2007. Prior to that, it was a family-run business. Our primary products are vertical machining centers, 3 to 5 axis, vertical CNC bed mills, flatbed CNC lathes, a BR series or bridge mill that we are using with M7 for laser scanning of larger prismatic parts, and we also have a partnership with another Minneapolis-based company for friction stir welding, and we're developing technology to do friction stir welding and metal cutting on the same machine. The reason that we are able to work with M7 is we have our own proprietary CNC control where the industry is basically standardized on a couple of controls, either Fanuc out of Japan or Siemens out of Germany or Heidenhain. We do have our own CNC control. It's a Linux-based operating system. We are MT Connect compliant, and for those not familiar in the machine tool industry, MT Connect is a protocol developed by our industry and standardized for communication.
All right, thank you, Paul. So here's a picture of one of his machines. It's a VM20 vertical milling center, 3-axis. And key features of the machine that we're interested in, of course, is a spindle. Every measurement that we make has to be referenced to the spindle or you lose right out of the gate. So our instruments are connected rigidly to the spindle. Since it's a 3-axis machine and we may want to inspect the sides, different contours of a part, we had to add in a 4th and 5th axis. We did that with an industry standard Renshaw PH10 head. A large part of my scanning time is spent waiting for the touch probe standard articulation tool, the PH10, to articulate to the next position. It takes almost, I can't make it go any faster than about 3 seconds, and I have to wait 5 seconds between moves. Next slide. So going back to what I said, I want to introduce you to the project. This is midway through the project, but I use this as a reference point throughout. I've got several of these artifacts out in the hallway. It's a simple machined blank. We want to be able to machine it, measure it, keep it simple at first. There's a sequence of pockets on there, 6 pockets going from 1, 2, 3, 4, 20, and 25 thousandths deep. And the colorization on this chart, that represents a 2-minute scan. That was 250,000 points captured in just over 2 minutes. The colors on the chart are keyed on the right-hand side to tell you how far from your model nominal position that measurement showed on the best fit characterization. Now, the next few slides, let me go back one, Jason, please. The next few slides represent a single axis, an X scan, okay, where the laser probe is looking straight down in Z at the part, and most all the data comes from right here within about 5,000ths of an inch of that edge, okay, the edge of the pocket. So now we go to the next slide. So to really study this, of course, you want to be able to measure an anomaly or a part feature, measure it in the same location, regardless of angle of approach, speed of approach, etc. And regardless of speed. And once you've done that, you should have pretty good confidence that you're measuring the anomaly, the feature, where it exactly is. So, like I said, this is the pocket, okay? It's 450 microns deep. It's a little shallow. This is the 20 thousandths deep pocket. This is the floor of the pocket. That's the top surface. This is the edge. That's the burr. There's these repeated anomalies here that I'll talk about in a minute. And there's this edge contour that we did not expect. Edge contour associated with a square end mill ought to be a square. We saw a slope. We're like, well, I don't know. You know, is that a laser anomaly, you know, due to a bending of light on a sharp edge? What is that? That's less than the thickness of a paper. From here to the ledge is less than the thickness of paper. And then we've got, what I was after is how much difference is there between locations of the anomaly, whether you moved it from left to right or right to left. So we got our measurement through this experiment. Next slide. We found out that we had a 32 micron shift that was constant. And then we ran an experiment at different speeds. This represents, the purple dots represent a slow scan where we're measuring 2 points every thousandth of an inch, actually measuring and recording 2 points for every thousandth of an inch of travel. 3 meters a minute, I get about 1 point every thousandth. 6 meters a minute, I get a point every other thousandth. And once we apply what we learned on the first slide, how well do all these measurements, regardless of speed and direction, how well do they line up? You can see they line up quite well. You can see I got the same slope. I have these little anomalies over here. Again, we're like, well, is this just a measurement anomaly? Do I filter it out because it's, you know, 3 standards of deviation away from my baseline measurement? What do we do with that? So, next slide. So we keep studying. So we run a whole lot of scans and overlay them all together. And each color represents 14 scans. There's a point in each color representing every micron of motion, 25 microns for 1,000th. The red scan is as machined. We have the same burr. You can see how sharp it is. I've got the same slope. We go over the part with a little peanut grinder with some emery on it. We knock that burr down, and look, we actually warm up the part. The part rises a little bit, and the burr doesn't completely go away. It lays down and shows me a different edge. And the whole green graph is just a few microns above my baseline red. We let it cool down for a little bit. I run it over with the scanner again. I color code that scan blue, and blue is very consistent with A. Okay, so now back to the anomalies. We're not sure, again, whether the slope is true, whether these fleas, I'll deem them, on the surface are really there. So we brought in a modern, what amounts to a scanning electron microscope, and we looked at the part. We measured a 20-degree slope. We could measure the exact same burr, and we saw particulate matter on the surface pretty much galling. It left a little a little flea on the surface. And of course, when we are picking up a point every thousandth or every half a thousandth, we'll pick up those little anomalies on the surface, and they'll be consistently placed in the scans. Okay, so now we know that I can put a laser inside of a machining center. Oh, you're fine. We can put a laser in a machining center. Now let's get to the current practices of model-based, reasons for model-based. Well, we like to make another part, so the guy's got to retrieve a drawing, right? Well, what drawing is it? You can see I've got some hand drawings in there. This is typical of U.S. manufacturing, right? This is Saturday after the Christmas party, so we had to get Jake to be on camera, not Jason. Is that drawing associated with that serialized part? Someone from NavAir mentioned, hey, we get a part off a plane and it don't match the drawing. Well, no surprise. The QC data, it's stuffed in a drawer upstairs with the lights off, and you might have something in the file cabinet, you might not. You dig through and you find it. Well, that's going to be a one-off record retrieval, right? You might be on site, it might not be on site. Well, if this gets damaged, and then what is the fidelity of the data you took? You know, you measure diameter, you measure it in 2 locations perpendicular to one another with a micrometer, is it oval, etc. The G code running a part, is it a matter of permanent record? Is it associated with a drawing or a revision? Is it associated even better with a serialized part? What if the G code was associated to the serialized part? What if you knew what machine ran each part? He was actually looking for the scan path that we had just run. He didn't have to act this out. He couldn't find the file. This is the scan path for the part we have outside. Okay, let's go to the next slide. Now the model. Is the model an engineering model? Is it a production model? Is it in between? It's all these models we talked about. How about the datums? Are the datums on the model the same as what we're using to machine the part? How about to measure the part? All these things matter, of course. So what we're doing here is setting up the 3 primary datums, and you'll see my scans. We record the scan path, we record the scan data. We know exactly where these datums are. And then is this model the basis of G code? Is it the basis of metrology? And again, is it a matter of permanent record? And what I suggest is it can be a matter of the permanent record, and you can't answer yes to all the other questions. Next slide. Wow. Let's go full screen maybe. The tool path. You know, when you run CAM, depending on whose CAM process you run, there's all kinds of optimization means, and you're going to have finishes and sealing characteristics with one machine tool path that isn't going to be associated with another machine tool path. If you get one you really like, you better know what tool path you ran. So I'd suggest that we record tool paths. You got to really dial down on what you hope to record and then make it interoperable so that you can hope to recover and repeat that one part in 20 years that you really like. That one sight on a gun that really worked well, whatever. So how do we deliver value to the enterprise with model-based scanning and measurement in situ in the machining center? First of all, I save machine time. I increase the throughput on a machine. As you can see, we established datums in about 20 seconds. I had 14,000 points, statistically significant. I know exactly where my datums are. And we go pick up a probe, and I'm cutting while we're probing over here. And that goes on for a minute. This scan can be part of the permanent record. It's easily retrievable. I'll show that in a minute. And again, the scan path is a matter of permanent record. You know, if you don't know where you're measuring, if the machinist is just picking up a shaft, he gets out a micrometer, he takes 2 readings, he says it's 1 inch in diameter, plus or minus 1,000th. You don't know where on that shaft. You're going to go try to repeat that measurement. It may not be repeatable. 20 years later, you're going to have wear and distortion on that part. You'd like to know where it's worn, how it's distorted. You might want to know what the chemistry of the metal has changed. You've got to have high fidelity data indexed to the model to be able to answer those kind of questions. Okay, next, please. The part's finally done. And like I mentioned, it could be an intermediate scan too before the final pass. But in this example, I said, okay, we're going to monitor, measure the primary features of the part, index together so we can see if this part is a go or a no-go. If it happens to be a no-go, the follow-on question is there enough material there to make it a go? I've got hours and lots of shop time invested in the part. Can I make it a go? You know, is it a yellow part? Can I make it a go? And if it's yellow, what features have too much material on them that I can shave off and make it a go? So if you do the in-situ measurement, we facilitate rework without breaking setup. If you record this data for the serialized part, it's in a matter of permanent record, and 30 years later, when you're trying to decide whether this thing works or not, or how do I reproduce it, you've got a shot. Some of the earlier presenters were talking about science, et cetera. Well, of course, you can't have science without data. You can't have engineering without science. It all builds on data, and now we have the enablers to really interrogate our components and get an incredible amount of data. And then in 20 years, when you're trying to decide why is this one different than that one, you've got something to make that decision on. Okay, next slide. So this is the data overlaid on the model. Okay, we were running our laser data, our raw laser data, into an industry standard software called Polyworks. Jason is an expert on Polyworks. He had to do this on Saturday night because Saturday morning didn't work out. There are 9 tip positions. If you understand that Renshaw PH10 head, there are 9 tip positions associated with getting these measurements. They all have to be indexed together quite precisely. That's our one opportunity right now for improvement, although they're already measured pretty well. Next slide. Already indexed quite well. This is one of our primary datums. I think the standard deviation on that scan is like 15,000 points there, and our standard deviation is around a micron. So 67% of the data is all within the mathematical plane describes the best fit of that set of data. Similar on these other points down here for the datum lines there. And then inside we measured the bore. I forget the number of points, but there's 6 elevations of scan, rotating 45 degrees on each. And then we go in and we scan the shoulder, again in 8 segments, just because the Renshaw is how it's set up. Next slide. Then when you get rid of the wireframe, you can see it a little more clear. This is the keyway. This is the base of the part. The primary feature, the bore carrying a bearing. Next slide. If I really zoom in close, you know, it takes several moves. If I really zoom in close on that top plane scan, I look at the point selection, okay? Now, our scan speed is 6 meters a minute. And in machining terms, that's pretty fast. It's not quite as fast as Curtis Toon's machine will run at BAE, but it's fast. And we're measuring and recording now 2,000 points a second. And what it amounts to at 6 meters a minute is we get a point recorded for every 2,000ths of an inch of travel. For every 50 microns of travel, we're recording a point. Now look how straight that, I'm sorry, but that's as broad as we can make it. But that is a straight line, a whole sequence of dots on a single scan. Looks good. Next slide. So now how do you, and this is a Polyworks non-optimized presentation, but how do you get that in front of the machinist? The part's sitting there. You did this scan. It took a minute or whatever. He's trying to decide whether he's going to load another rough or if he's going to touch this off and make a yellow part into a green part. And so when we look at this, we say, well, this datum is flat enough. This keyway is a little shallow. We could touch that off, make it better. This cylinder, it's located okay, its diameter is okay, and if we back up one slide, 2 slides maybe, one more, we'll see that this colorization isn't by accident. Let's go forward again. There's a zone in there that's not perfectly perpendicular with the z-axis of the machine or the z-axis of the part, and we're measuring about a ½ degree out of position. Now this is a precision bearing holder. It's got to be spot on, plus or minus, so that could be touched out. So, you know, instead of this part either going into service in production, causing a failure on the line at US Steel or wherever it's at, it's caught, it's corrected, and it goes into service as an ideal part. Now, we're not relying on first article inspection. We're going to run one part every 100, and when the 100th part fails, you're like, oh, how bad was it, right? You're measuring every single part. Seems like a better way to go to me. Next slide. I mentioned we had 9 tip positions, so I've got to index them all together. We made scans in 9 positions, and this is how they present in PolyWorks, spatially oriented in the machine tool before they're corrected for the tip position. And then I come up with offsets for each tip position relative to straight down. It allows us to tie it all together. Next slide. So, you know, how to deliver value to the enterprise is we fade out these scenes and we fade in a scene where each part has its own serialized data reference, and it's on the part. Could be a QR code. I used a QR code. You can scan this QR code right now. It will link you to a file on M7's website, and you'll look at the same scans that we just made. You'll be able to read the Metrology machine original quality control documents, you know, the X, Y, and Z linearities, etc. You'll be able to see that when I ran a ball bar on that machine and looked at the backlash, the reversal errors, the squareness errors, etc., it's not up to speed today. A lot of us in industry are running around believing that that machine that we bought a few years ago is still a perfect machine, and it's not. And so I think that some system like this, where each part had its own way to refer back to its technical data package, not a technical data package for the F-14 fighter, but for a serial number of the F-14 fighter that's been updated every time a mechanic touches it. Every time a new part goes on it, it could be updated. Next slide. So in summary, we believe that quality improvements can be made, substantial quality improvements can be made with in-situ metrology. Fast non-contact laser probe is just one sensor. We're talking about integrating ultrasonic, so you can do a 3-dimensional scan and register all the voids, inclusions, etc. in your component, send it out to service, measure them again, see if a crack is growing, eddy current, XRF, you know, so you can check later in life if the part wore, where it wore, if it's strained and permanently was deformed, how it was strained. If you had a crack propagate, is it still within design allowances or not? And knowing how that crack propagated will teach you how to design a better part, how to specify a better part. And of course, this is disruptive. It's going to modify workflows. It's going to impact electronic documentation. In 2013, we'll be doing beta sites outside M7, the first of which is Miltronics. As Paul mentioned, he's incorporating a laser on one of his, is it BR? BR series bridge machines, and to help us out, he's putting on consignment a brand new machine in my QC lab at M7, modified with glass rails so I can have the maximum machine accuracy possible instead of encoders based on the servos. Now this will let us stretch to the limit, today's technical limit, the accuracies and registrations of measurements we can do on our machining centers. All right? He skipped 2. I'm ready for questions. Yes, sir.
On the feedback loop that you had, where you were showing what was, good and bad, green and red.
Yep.
How did that work? Was it Polyworks?
It's very much manual right now. Of course, I can present it in a half hour and make it go quick, but we're working with the metrology software providers that can automate that. And my vision is that the machine tool operator is going to get an image of the model on his screen. The features that are good are going to be green. If the part's recoverable, it's going to be yellow. If it's a go, there'll be a big green bar there, there'll be a yellow bar there. If it's completely reject, there's a red bar there. It goes to the scrap bin. And that QR code, that scan serial number is always associated with a reject. So it should not ever be placed into service. Any other questions?
The logic for every certain type of out of tolerance, just retool it on the spot? Or
Yes, sir. Yes, sir. That's the intent.
Okay.
That is the intent.
So that's the software logic, CNC, combining the two sides of the equation,
Yeah.
the probe and the milling.
Now, to do that, you're scraping a couple thousandths of material off. And if you're familiar, it's a lot easier to take off 7 than it is 1/1000th of an inch, right? It's a hell of a lot easier to take off 7 than 1. So you're going to have an awful lot of science behind that path